students, it's me Saurabh Kumar, BTech and MTech Electronics and Communication Engineering from Delhi campus. I am associated with askIITians as physics mentor. We are going to discuss electromagnetic induction, its application in daily life. We have seen the best example as induction motor and electric generator in which mechanical energy converts into electric energy, and that involves magnetic flux, induced EMF, induced current, eddy currents, types of electromagnetic induction as self-induction and mutual induction, energy stored in a coil, and the concepts based on self-inductions. We divide the theory section of electromagnetic induction into various parts, and in the first part we will discuss about magnetic flux and then laws of electromagnetic induction by Faraday's. Let's start with the topic electromagnetic induction. In this topic, we will discuss about the phenomena of inducement of current and EMF across the coil connected. So, the topics involved in this the first one is introduction, magnetic flux, Faraday's experiment, Faraday's laws and applications, Lenz's law, motional EMF, types of electromagnetic induction, self-induction, mutual induction, and that after this we will discuss energy stored in an inductor. So basic introduction, we will discuss about what is magnetic flux, what is magnetic field, and how that magnetic lines of force passes through the area of a closed loop. In case of magnetic flux, we will discuss about this, the flux due to the magnetic lines of force. After this, the application part involved with the concepts of Faraday's. Faraday reduces two laws. First law related to the inducement of current or EMF across the coil connected with it, and its applications like lightning of a bulb connected across a moving coil across any magnet we considered. In the Lenz's law, we will discuss about the direction of induced current in the secondary coil. After that, we will discuss about motional EMF. So, we must understand EMF is due to the magnetic flux change with respect to time t, and this motional EMF is associated with the motion of the coil or magnet respective to the stationary coil or magnet we considered. Now, in this case, we will discuss when the coil is moving with velocity v of particular length L, the EMF induced in the secondary coil would be of particular value is under this motional EMF. Now, type of electromagnetic induction. Electromagnetic induction, we will discuss, these are of two types. First is self-induction, second is mutual induction. And after this, the topic involved with the energy stored in the inductor, means energy stored in the inductor of self, if it is a self-induction, means single coil, energy stored across this, or we can say the work done phenomena. Now, the topic is application of self and mutual induction. The basic example, basic application involved with the generator part and the induction motor. Now, as a drawback, eddy currents, when current passes through any metallic substances due to the inducement, there are some eddy current produced, and these are harmful. So we use some applications to avoid these eddy currents. Now, how coils are connected, like series or parallel, and after this we will discuss about electric generators and applications, and then transformer, step up and step down, and then we will discuss induction stove. So the first topic is introduction part. So in the introduction part, we know that whenever an electric current flows through a conductor, it is due to the magnetic flux line passing through the area of the closed coil, and there is a galvanometer. So galvanometer shows the deflection. This is what the magnetic field, this is the coil. So we know that when we bring this magnet near the coil, area enclosed this is just changed. So what? There is current induced, and this deflections reflect by the galvanometer connected across the secondary coil. So we can say, it can be said that when electrons are in motion, it means we are talking about electric current, and the phenomena whereby an EMF or hence current is induced in any conductor which is cut across or is cut by magnetic flux is known as electromagnetic induction. So this is just the basic introduction about this chapter, bringing a magnet into the area of a coil, some induced EMF with induced current reflect by the galvanometer connected across the secondary coil, and this is electromagnetic induction. Now we must understand what is magnetic flux. The magnetic flux is actually the lines of magnetic field passes through an enclosed area. So flux is associated with the effect that is passing across an enclosed area. It can be the case of electric, it can be the water flux, it can be the fluid flux. This time we are talking about magnetic flux. So it is given here a measure of the quantity of magnetism being the total number of magnetic lines of force passing through a specified area in the magnetic field, and that is denoted by phi is equal to B into dA. And we know that V is a vector quantity, area is itself a vector quantity. When we find out the dot product of these two, we are getting that is equal to integration of B dA cos of theta. So we can say this line A represents the normal vector of the area, and blue line represents the magnetic field. So there is an angle between them is theta. So we can understand, or we can represent the case like this. If this is area A1, this is area A2, its angle is normal direction radially outward, that is AN cap, and it is just AN2. Now, when we allow magnetic lines of force from port A1 to port A2, then the angle between this B and A1, angle between them, this angle is actually 180 degree, means pi. And this is making angle theta degree over here. So we can say the theta between them is theta. So we can find out the flux exit point is equal to B into A cos of theta of this section. So there are lots of examples that can be covered into the magnetic flux. So we must understand the formula for magnetic flux, that is this. Now we must understand what is the unit to specify magnetic flux. Usually we define it by the quantity, by the unit Weber, but when we want to describe in terms of magnetic field strength and the area, it must be Tesla meter. Tesla meter square. Tesla is for magnetic field, meter square is for area. So this is under magnetic flux. Now we will discuss about magnetic flux in a non-uniform field. So somewhat it is given, the magnetic field is not uniform, it is changing with respect to length or with respect to time t. So then we consider a small area, through which magnetic lines of force passing through that. So in these type of problem, magnetic flux may be a function of linear equations, linear variables like distance, length or breadth, or maybe the function of time. It means magnetic field is changing with respect to time or position. So when we want to find out magnetic flux across the closed loop, it would be equal to magnetic field at that moment. It may be the function of time, or we can say B as a function of x or y into the area dE. This can be x into dy or y into dx. What I am considering x and dy. Actually, we can consider this part, length means this is your x and it's your y. So means if I am considering a small segment, so this it would be of length dx. So area will be equal to dA will be y into dx. Or if we want to consider the length along vertical direction or along y-axis, it would be dA is equal to x into dy. The main point is if magnetic field is changing with respect to length or breadth or with respect to time t. So we need to consider a small area through which magnetic lines of force passes. Now Faraday's experiment. Faraday's predicted some experiment in 1831. He find out that when there is relative motion of this magnet into the coil that is connected with the secondary wire, and that wire is connected with the galvanometer wheel. It may be ammeter, it may be voltmeter. Voltmeter connected in parallel, ammeter connected in series. But to show the precise and accurate value of electric and magnetic field, we are using galvanometer. Now, there is relative motion of this magnet into the coil. We found that area is changing, means magnetic field strength is changing. So we must understand phi is equal to B into E. So we know that this magnetic field strength is changing, means initially it is at a distance over here. So we can say the magnetic strength at this distance x1 is different than the condition reflected over here. So it is into this one. So we can say the magnetic field is changing into the coil area. It is giving us the induced EMF. So we must understand E is equal to change of magnetic flux with respect to time, or we can say that is B into A upon delta T. Delta is the change in the quantity, and this time magnetic field is changing with respect to time T. Area is remain constant. So the deflection produced, it is just the EMF, and it is of opposite nature, and due to that EMF there could be some current. Now second point, it also depends on number of turns. It also depends on number of turns. If we are considering this one loop through which magnetic lines of force passing, so we can say phi is equal to B into A. If there are n number of loop over here, so we can say the net magnetic flux is equal to n into B A. So this is the net flux. So it depends on the number of turns, magnetic field strength, and the area. Now next point, the important conclusion involved in this. So Faraday find out some important conclusion after this experiment, like the galvanometer showed deflection. Galvanometer showed deflection whenever there was a relative motion between magnet and the coil. Relative motion between the magnet and coil means we are talking about the change or the variation in the magnetic field strength across. So if we consider this is a coil and we are bringing some magnet, so at a particular means there should be a relative motion. There should be a relative motion. If you stop this magnet over here, there could not be any EMF or current induced in the secondary coil. So there should be a relative motion, means there should be change in the value of magnetic field. You bring it and just take it away like this. Now we would like to discuss the deflection was more when relative motion was faster. Means if there is just quick variations in the magnetic field strength, that gives quick variation in the magnetic flux, and definitely the value of EMF will be according to that. Now the third point, the direction of deflection change if the polarity of the magnet was changed. Of course, means when we are taking north pole towards the coil, we found the induced current would be of unipolar. But when we change the polarity of magnet, we are taking magnet away from this, so it will show the deflection produced in the galvanometer will be in opposite directions. It's like that. It is changing the polarity. Means that's why we can say current showing over here is bipolar. Taking magnet towards the coil, deflection shows by galvanometer would be towards right. When you take magnet away from it, it shows deflection towards left. So it means it shows polarity according to the moment of magnet. Next thing, that is the deflection in the galvanometer changes with the change in the number of turns of coil more than so means more the number of turns, greater would be the deflection. So deflection is actually for current, and current is due to the EMF produced divided by the resistance, and this EMF is due to the change in magnetic flux phi with respect to time t. And we must understand this magnetic flux depends on the magnetic field strength, area, and number of turns of the secondary coil. So that's why we can say number of turns n. Means you have seen many cases in transformer. If we are using coil of large number of turns, definitely current induced would be more as compared to the single turn coil. That's why we prefer unbreakable turning coil. So these are the topics involved over here. Now we will discuss some problem based on these concepts. The first question is, the induced EMF in a coil rotating in a uniform magnetic field depends on. First of all, we must read the question again. The induced EMF in a coil rotating in a uniform magnetic field depends on. So we must understand this EMF is equal to the change in magnetic flux and its magnitude. Basically, we must understand B into area divided by time t. So mean if magnetic field is uniform, definitely area is changing. So we know that if we consider this is in a coil rotating in a uniform magnetic field, if it is rotating with certain angular velocity omega, so we found that area is considered, that is equal to VL omega square by 2 if there is a drop swapping sum. But if we consider, so simply we can find out the area swap. So finally we are getting EMF depends on number of turns, also the magnetic field strength, also area. So it depends on only on the total number of turns in the coil? No. Only on the magnetic field? No. Area of the coil and speed of the rotation? No. All of the above? Yes. So it depends on magnetic field strength also, number of turns also the velocity, means that is a function of angular velocity. So we can say this EMF produced across the coil depends on the magnetic strength B, number of turns, and the speed with which it is rotating. So option D is the right answer. Example number 2. A uniform flux density 0.1 Weber per meter square extends over a plane circuit of area this and is normal to it. How quickly must the field be reduced to 0 if an EMF of 100 volt is to be produced? So first of all, we must note down the given values. Given values, uniform flux density. So phi is equal to 0.1 Weber meter square. Flux density, this one, extends over a plane circuit of area. So area is given as 1 meter square, normal to it, this one. How quickly must the field be reduced to 0 if an EMF of 100 watt to produce? So we want to produce EMF that is of 100 volt over here. So we can say E is equal to change in flux with respect to time t, this one. So uniform flux density, this is the magnetic field we are given. So phi, so we can say that is V into delta A by delta T over here, and in this way we can find out B is given, delta T is given, so that is 100 watt is equal to 0.1. Now area is what? Area is changing, how quickly must the field be reduced to 0. So mean we need to consider it like that. We know that when it is changing, E is equal to delta phi by delta t, or phi is equal to B into A cos of theta, or we can say B into cos of omega t. When we want to differentiate this function with respect to time t, we are getting this is equal to B into A into also the number of times we will multiply over here, and then tan into sine of omega t, and the negative of this value and then its magnitude is given in this one. So we want to know how quickly must the field be reduced to 0 if the EMF of 100 volt is. So means initial value and finally we will put over here, this is this, how quickly, and area is 1 meter square upon time t. We will put the value t is equal to 0.1 divided by 100, and simply we are getting is equal to 1 into 10 to the power minus 3 second. So mean we will use the basic formula that E is equal to minus delta phi upon delta t over here, and this question is based on this concept. Now we will discuss. In this part we discuss electromagnetic induction and Faraday's laws of electromagnetic inductions. Now we are going to discuss Faraday's laws of electromagnetic induction and its applications along with the concept of mutual induction. So stay tuned with us.